So we now start the second talk for the day in the fractional calculus seminar series. For the second talk, we have Professor Bernt B.Øksendal. He is a Norwegian mathematician with several years of teaching and research in stochastic analysis. He completed his undergraduate studies at the University of Oslo in 1970 and obtained his PhD at the University of California, Los Angeles in 1971. In 1991, he was appointed as a professor at the University of Oslo. In 1992, he was appointed an adjunct professor at the Norwegian School of Economics and Business Administration, Norway. In 2017, he was appointed an honorary doctor of the Norwegian School of Economics. Between 1992 and 1996, he held a research position as Vista Professor appointed by the Norwegian Academy of Science and Letters in cooperation with then Norsk Statsopplyser. In 1996, he was elected as a member of the Norwegian Academy of Sciences and Letters, and in the same year, he won the Nansen Prize for his research in stochastic analysis and its applications. In 2002, he was elected as a member of the Royal Norwegian Science Society. In 2014, he was awarded the University of Oslo Research Prize for excellent research. He has also been the chair of or coordinator of many research grants and international research programs both in Europe and Africa over the years. It is nice having you here, Professor. You may please begin your talk.
Thank you very much for this kind introduction, and thank you for the invitation. Can you all hear me now?
Yes, we can hear you.
Okay, so the title of my talk is the stochastic heat inclusion with fractional time driven by time-space Brownian and Levy white noise. So it's a joint work with Olfa Drawil and Rama Yasmina Muley Hachemi. So here's an abstract of the presentation. So we study a time-fractional stochastic heat inclusion driven by additive time-space Brownian and Levy white noise. The fractional time derivative is interpreted as the Caputo derivative of order alpha in the interval from 0 to 2. So we show the following. If a solution exists, then it is a fixed point of a specific set-valued map. Conversely, any fixed point of this map is a solution of the heat inclusion. Finally, we show that there is at least one fixed point of this map, thereby proving that there is at least one solution of the time-fractional stochastic heat inclusion. This is here we are working in the general stochastic distribution sense. So it's also interesting when we can represent the solution in usual L2 form or LP form. So in part D here, we say that the solution y of Tx is called mild if the expected value of y squared is finite for all t and x. And we show that the solution is mild if alpha is 1 and d, the dimension, space dimension is 1, or if alpha is greater than or equal to 1 and the dimension is either 1 or 2. On the other hand, if alpha is less than 1, we show that the solution is not mild for any space dimension. And we give two examples, one with numerical calculations and figures. I think maybe the concept of a differential inclusion is not familiar to all of you. So let me give a very preliminary introduction in terms of explaining what is a differential inclusion. So roughly, a differential inclusion is a set-valued differential equation. It's perhaps best explained by the following simple example. Consider this differential inclusion. So we want to find a function f such that the derivative of f is in the interval between 0 and f of x. And we normalize it to say that f of 0 is equal to 1. The problem is that the set from 0 to f of x depends on the function we are searching for. However, in this case, we can avoid the problem by first dividing by f of x to get that the f derivative of x over f of x belongs to the interval 0, 1. And that means that the derivative of the log of f of x is in 0, 1. And then we can integrate this, and using that f of 0 equals 1, we get that the log of f of x belongs to the integral from 0 to x of the set, the interval from 0 t dt. So it's a set-valued integral. So it's defined to be the collection of all integrals from 0 to x of g of t dt, when g is an interval between 0 and 1. And that means that the general solution, of this inclusion is that f of x belongs to the family of exponential of integral from 0 to x of g of t dt, when g over the family of g of functions g between 0 and 1. So typically, solution of an inclusion is not just one function, but a family of functions. Okay, but in this presentation, we study fractional stochastic heat inclusions, which can be used to model the transport of substances in porous and fractal media, subject to noise and uncertainty. So possible applications include fluid flow in porous rocks, such as in the following example. Contaminant transport in fractured aquifers. A fractured aquifer is a groundwater system where the water with contaminant migrate primarily through rock cracks or fractures in rocks, as well as through porous media like sand and gravel. So the model we use to describe this is the following fractional stochastic heat inclusion. So on the left-hand side, we have the Caputo derivative with respect to t of y of dx. So t denotes time, and x is a space variable. That should belong to the this should not be this the Laplacian of y plus a function plus a set g of y of tx plus sigma w of tx. This is I'll come to that, plus gamma v of tx. And with the boundary conditions at time 0, we have the measure at x, and the limit when x goes to infinity in absolute value is 0. So here, this d alpha, dt d alpha represents memory and anomalous diffusion. When alpha is less than 1, it's subdiffusion, and when alpha greater than 1, superdiffusion at time t and in position x. So this is important in fractured system where movement doesn't follow normal diffusion. Also, we can explain trapping and release of memory effects when the pollutants are trapped in fractures for days and then released suddenly. So that's the point with these noise terms that we have here, W and V. So the delta, capital delta, denotes the Laplacian operator defined by 1, 4 as usual. And this g of y of tx in this example, it could be just k1 times y of tx, k2 times y of tx. So there's an interval. So that represents, since we have a set here, it represents uncertainty of absorptions rate. For example, low absorption limestone, K1, versus clay layers of high absorption, K2. This sigma W, sigma is just a constant. The W represents microscopic permeability fluctuation. This is the Brownian white noise, W. And the V represents sudden jumps from fracture activation. And this is represented by the Levy white noise. I'll come back to that later. And the boundary conditions, that the value at time 0 is the Dirac measure, represents the instantaneous release of the contaminant at x equals 0 in this case. Now, I will come back to a similar example or another example in the last section. And there we also do some numerics and figures to explain this. Some mathematical details of the model, to be more precise here. We will be working in the space S star. This is the Hida space of stochastic distributions. And y of tx, y of tx omega, omega indicates that it's a random process, is an S star valued process. And G is a map from S star into the set of Borel subsets of S star. And then the equation that we study is that the Caputo derivative of y should belong to this Laplacian of y plus this, here's the set G of y of tx, and sigma w plus gamma v. So this is sort of representing the uncertainty in the model. For example, it could be with a certain interval of values. And d will denote the space dimension, and x in Rd a point in space, and the t the time, and again d alpha dt alpha is the Caputo derivative of order alpha. Sigma and gamma are given constants, and the Laplacian is like that, as mentioned before. And now the W is the Brownian white noise. So this B is the Brownian sheet in 1 plus d dimensions, and we take the derivatives with respect to time t and with respect to the space variables. So this is the representation of the Brownian noise. So B itself is this Brownian sheet and we have a probability log p for that. And then the V similarly will be the derivative of the Levy process. So L itself is a 1 plus d parameter Levy sheet, and the boundary conditions as before. So the remark here that the W and the V, they model two different types of noise, which both can be represented as elements of the Hida space, or Hida Levy space, maybe in this case, S star. So it's a space of stochastic distributions. W is continuous Gaussian noise, while V of Tx is noise coming from jumps from a Levy sheet. So this will be explained a little later. So what do we mean by a solution of such a fractional stochastic heat inclusion? We say that y of Tx is a solution to the fractional stochastic heat inclusion 1.5 if there exists an adapted, this is the filtration generated by the Brownian sheet and the Levy sheet, and the S star valued stochastic process, G of Tx. There exists such a G of Tx such that y satisfies the equation d alpha dt alpha is equal to Laplacian of y plus this G of Tx. So we take a selector from the space here, and then sigma w and gamma v. So here we are an equation and not an inclusion anymore. So y is the solution of the original inclusion if there exists a G with values from the capital G such that this equation holds. So it's a little more about the model itself. In the classical case, when alpha equals to 1, this equation models the normal diffusion of heat in a random or noisy medium. Noise being represented by the time space white noise W and B. When alpha is greater than 1, the inclusion can be used to model super diffusion or enhanced diffusion. where the particles spread faster than in regular diffusion. For example, this may occur in some biological systems. On the other hand, if alpha is less than 1, the inclusion models subdiffusion, in which the times of travel of the particles are longer than in the standard case. Such a situation may occur in transport systems. In all cases, the drift term, this set G or Y or Tx, so there is a set depending on the Y, represent a sink source of the system. It is set valued because it models an uncertainty in the possible values it can have. Now we consider this inclusion in the HIDA space as star of stochastic distributions. And then in theorem 5.3 later, we show that an S star valued solution, if it exists, must be a fixed point of a corresponding set valued map. And conversely, any fixed point of this map is also a solution of the fractional heat inclusion. Then we show that there is at least one fixed point of this map, and we conclude that the fractional heat inclusion has at least one solution. What kind of solution do we get? I mean, in general, we just get a stochastic distribution solution, but the solution might be mild in the sense that the Y of Tx is actually in L2 with respect to the probability law of the processes. Now, it's well known in the classical heat equation case, with alpha equals to 1, a solution is mild if and only if the space dimension is d equal to 1. Now, in our inclusion setting, not equation setting, we show that if alpha is in the interval from 1 to 2, the solution is mild if d is 1 or d is 2. So 1 or 2 space dimensions is nice. And then if alpha less than 1, the solution is not mild for any space dimension. So in next section, we give some mathematical preliminaries. And then in section 3, a short review of the well-known white noise theory based on multi-parameter Brownian sheet. And in section 4, we present a white noise theory based on the multi-parameter Levy process or a Levy sheet. Now, this appears to be new, and we have not been able to find it directly in the literature. Section 5 then contains the main result, a solution of the fractional stochastic heat inclusion, given by Brownian and Levy white noise. And then in section 6, we studied this question about mildness. And finally, in section 7, we present another example of application, where we include numerical calculations and figures. So okay, so some mathematical preliminaries. I will be very brief, but just mention for the notation that we will need later. For example, we need the Mittag-Leffler functions. And here's the definition of that. The two-parameter Mittag-Leffler function with two parameters alpha and beta is denoted by E alpha beta of Z and defined by this expansion, here's expansion. Well, in general, this set and the alpha and beta can be complex numbers. The real part of alpha is positive, and the real part of beta positive. And gamma is the gamma function. So we can say regardless an enormous generalization of the exponential function. In the one parameter case, we have for a given alpha, we have E of alpha of Z defined by this here's expansion. It turns out that this will appear naturally when we study Caputo time derivatives. So come back to that. So here's the Caputo fractional derivative, which is probably very familiar to all of you. So d alpha f of x is given by this integral expression. if alpha is not an integral. And if alpha is an integer, it's given by the normal derivatives. So for example, if f of x is x, the identity function, and alpha is 1/2, with the 1/2 fractional derivative is 2 times the square root of x over square root of pi. And then we need to apply Laplace transform and see its connection to Caputo derivatives. So here's the usual definition of a Laplace transform, L. L applied to f at s is this integral from 0 to infinity, e to the minus st f of t dt. So it's f tilde of s. Some useful properties is that Laplace transform of the Caputo derivative of f is it's given by this combination of powers applied to the Laplace transform of f minus f of 0, s to the alpha minus 1 f of 0. And the Laplace transform of the Mittag-Leffler function with parameter alpha applied to b of t to the alpha is given by this expression. And we also list this, that the Laplace transform of this power times the alpha, well, in this case, alpha is equal to beta, then the Mittag-Leffler E alpha alpha at minus b t to the alpha of s is 1 over s to the alpha plus b. So here's the convolution of two functions. We define it like that. And the convolution rule for Laplace transform, is that the Laplace transform of a convolution is the product of the Laplace transforms. Or written in another form, that if we take the convolution, it will be the inverse transform of the product. And then we come to integrals of set-valued functions. So we have this definition here. Let G be a function from R into the family of Borel sets, set-valued function. And then you define the integral of G, the integral from A to B of this set G of t dt as the family of all integrals where G belongs to this boldface G. This boldface G is the set of all integrable functions, such that G of t is in capital G of t for all t. So this is the definition of integrals of set-valued functions due to Allman. So this will be adopted at addition in our study. And then the Laplace transform and Fourier transform of a set-valued function is then defined using this Allman definition of integration in the natural way. And the Fourier transform similarly. Fourier transform of G at y, denoted by G hat of y, is the integral over Rd. E to the minus I is the square root of minus 1, the imaginary unit. So e to the minus I xy G of x dx. Now G is a set, capital G is a set. So again, this is the family of all these integrals where G belongs to this boldface capital G. Or briefly, it's a family of G hat of y. Then we come to time-space Brownian white noise, and it's of course a big chapter if we go into details, but let me just mention very briefly. It's a construction of the Brownian sheet and the corresponding Brownian white noise using the Bochner-Minlos theorem. So then we start out with the n greater than 1, a fixed natural number, and later we will put n equals 1 plus d. So 1 will be the time, and the d will be the space dimension. So we define this capital omega to be this Schwartz space of tempered distributions on Rn, equipped with the weak star topology, and this space will be the base of our basic probability space, which we explain here. So as events, we will use the family of Borel subsets of S prime, and our probability measure boldface P is defined by the following result. So there's the Bochner-Min loss theorem. There exists a unique probability measure P on the Borel sets of S prime with the following property, that the expectation, dE denotes expectation of e to the I, and then phi applied to, well, omega if you like. If here is specified like that, the integral of e to the I omega phi, dp of omega, is equal to 1/2 times the L2 norm of phi for all phi in S of Rn. So this is the space of test functions. And then this omega phi, or written like that, is the action of an omega tempered distribution on a phi is a test function. So there is such a measure with this property. And this is called the white noise probability measure, or the Brownian white noise probability measure. It's often used, also called the Gaussian measure on S prime. And then we can proceed to construct the Brownian sheet by simply applying omega to the indicator functions. Then this B tilde defined like that will have a continuous version, which becomes an n-parameter Brownian sheet. And what we mean by that, we mean the process satisfying these conditions. So I just say that it's a generalization of the Brownian motion, which is familiar to most of you, to the case when we have multi-parameters, so a multi-dimensional time, if you like, or time-space Brownian sheet. So for n equals 1, as I just said, we have the classical one-parameter Brownian motion. Now we can then proceed to define the n-parameter Wiener-Ito integral by saying that the integral of phi of x dB of x is simply omega applied to phi. So we see that by using the Bochner-Min loss theorem, we have obtained an easy construction of n-parameter Brownian motion, or sheet, that works for any parameter dimension. Moreover, we get a representation of this underlying probability space omega as the dual S prime of the Frechet space S of Rd. And this is an advantage in many situations. So we have some structure on the omega, and that can be used, for example, in the work of on Mariava derivatives. So now in the following, we put n equals 1 plus t, as I mentioned, and then b of tx is b of tx omega, is the one-dimensional time-space Brownian sheet with probability. It's one-dimensional, but it's multi-parameter. So the value of b is in R. Now, since this process is almost surely continuous, we can define its derivative with respect to t and x in the sense of tempered distributions. However, this we cannot do when we come to Levy processes later. So we will put both of these in the space S star because of that. Okay, so then this W then is this derivatives with respect to time and space of the Brownian sheet, and in the one-dimensional case, it's the usual. Then it will be an S prime, and similar for Levy sheets, we will have a similar kind of derivative. Now, so here we come to actually something which is deserves much more time than I can give now, but we need to construct a similar type of the process or a sheet, coming from the Levy process, as we do for the Brownian motion. And we obtain this by combining results in several papers from Ifrata and Rikutu, and from Dalang and Walsh, Dinuno and co-authors, and Proske and myself. There is also an earlier paper by Adler and co-authors. You can find all this in the literature in the end. So I think I will be very fast here. Just say that a multi-parameter Levy sheet is a stochastic process, L, or it should be L of x omegas and misprint there, satisfying the following conditions that start at 0, L of 0 is 0. L has stationary independent increments with respect to the natural partial ordering on Rn. Now, of course, now the time, if we like, is multidimensional, so we don't have a linear ordering anymore. We can still talk about independent increments. L is continuous probability and has a Cadillac path, so continues from the right and limit from the left. So, for example, we have this definition of a box or rectangle in Rn plus, and this is here in the case n equals 2, defined that the Levy process value at x1 prime, x2 prime, minus the V process value at x1 prime, x2, minus L of x1, x2 prime, and then plus L of x1, x2. I should have a figure here maybe to illustrate it, but this is a natural box, you know, with these corners. Now note that in general, then this process is not continuous, but if it is continuous, it coincides with the Brownian sheet we had before. So very quickly, then let R denote the box in R plus n, and let U be a Borel subset of R0, which is R minus 0. And then we define the jump measure, n of Ru, to be the number of jumps of L within the rectangle R of jump size in U. So by stationarity, this map R goes to n of Ru, only depends on the volume of R, and we can write the random measure generated by Ru going to the number of jumps Ru in the differential form as n of dx du. So it's a random measure. And then this expectation, if we put R1 is 0, 1 to the end, the unit box, this measure sending U to the expected value of n of R1U. So this is the expected number of jumps within the box R1 or jump size in U. This is called the Levy measure of n. And then the corresponding compensated jump measure, n tilde dx du, is the jump measure itself minus the Levy measure times the Lebesgue measure, where dx is dx1, dx2 up to dxn. And then we will, in the following, assume that the integral of z squared nu dz is finite. This is to be able to put everything into an L2 concept and to context. So it's and then it's sufficiently general for the applications we have in mind anyway. Now, in the general, by the Levy-Chinchin theorem, the Levy sheet L can be given the following general representation. They all look like this. So L is alpha times the product of the coordinates plus sigma times Brownian sheet, plus this integral with respect to the compensated Poisson random measure, where alpha and sigma are constants. And in the special case, when alpha is equal to sigma is equal to 0, we call L a pure jump Levy sheet, and it has this representation. So this is the case we will concentrate on, because we already have covered the Brownian motion in part in the other section. So we will now just add the pure jump Levy sheet. And then, well, I don't have time to do all this, but now we can proceed as we do in the Brownian motion case and construct the white noise corresponding to the Levy sheet. So I will just skip that and come to the heat inclusion. The fractional stochastic heat equation. So we are now ready to state and prove our main results. But first we need to recall the definition of Hausdorff distance d of x comma y between two subsets x and y of a complete metric space set with distance metric d. So the distance between the set x and the y is the maximum of this supremum and this supremum, where this first here is the inf over y in y of d of xy, and d of yx is the inf over x in x of d of yx. And we need this for the uniqueness of the fixed point. So we say that an S star valued process y is adapted if the stochastic process obtained by applying y to a test function is adapted for all test functions. And then we have the following theorem. Let G now be a set valued function, and let boldface G of y denote the set of all selectors of G of y of Tx. The set of all S star valued functions little g, such that little g of Tx belongs to capital G of Tx for all T of x. So assume that all elements of the set boldface G of y are adapted processes with compact support, and this map y goes to G of y is continuous as a map from S star into S star equipped with the Hausdorff metric. Then the following holds. Part 1, if y is a solution in the sense of distribution, more precisely S star, of the fractional stochastic heat inclusion here before, then y is a fixed point of this inclusion, that y of Tx belongs to I1 of Tx plus I2 of Tx y of Tx, and plus I3 of Tx. So it's a fixed point because y, we have y here and also here. This I1 is just, well, here we have the Mittag-Leffler function again. So we've written out, it will be like this. And I2 to pi to the d times I2 will be here. This set, it's set of all these integrals over all g in the capital G by the Aumann definition of integration of set. And I3 it will be a stochastic integral, but here, there is no y here. So going back a little bit, we see that it should be y should be a solution of this inclusion. This doesn't depend on y. This doesn't depend on y, but I2 depends on y. This is set. Conversely, then if y is a fixed point, then y is a solution of the fractional heat inclusion. So it goes both ways. And then by using the Caputani fixed point theorem, we will prove that there is at least one fixed point of this inclusion. So, okay, if there is at least one fixed point of the solution, there is also at least one solution of the heat inclusion. And let's see how much time I have. Not very much. I don't have time to do the proof. I think I will just skip that. And just
additional 5-10 minutes should be fine.
Yeah, okay. Yeah. but I think I'll go to mildness. So in the previous section, we proved that there is at least one distribution valued solution Y. And we defined then a solution to be mild if that solution actually is in the L2 space. So are any of these solutions mild? And this question has been discussed in the fractional heat equation case in the paper 17 with Jasmina and me. And then in that paper, the following theorem is proved, that Y be a solution of the fractional stochastic heat equation given by this. Then the following holds. We have these consequences then. Now, if we return to the inclusion case, we have Y of the form I1 plus I3 plus I2. And we want to study when the right-hand side of the equation belongs to L2. And now I1 plus I3 corresponds to the same term as in the previous paper. And by replacing the Brownian noise in this paper with the general Levy noise, we get the same conditions on alpha. So actually we get this result here. Alpha equals 1 and D equals 1. We have mildness. Alpha is greater than 1 and D equals 1, D equals 2. We have mildness. But if alpha is less than 1, then there is no chance of getting mildness for any dimension. So let's come back. Let's illustrate how we can apply these studies then. It's how theoretical results, which combines fractional derivatives, set valued maps, and Levy noise can be used to describe how nitrate pollution spreads through sandy groundwater systems. So sandy aquifers are made of loose or compact sand that allows water and dissolved substances to move through tiny pores between the grains. So these systems are common in many parts of the world and are easily vulnerable to contamination from agricultural activities, such that the overuse of fertilizers. So we focus here on the transport of nitrate, a highly mobile and widely observed groundwater pollutant. And our model is based on this fractional stochastic inclusion, same as we had before, with the same boundary conditions as before, and we are specifying the G. We'll come back to that a little bit. Again, the interpretation of the alpha is the same as before. The G is the interval from K1y, between K1y and K2y. That represents uncertainty in nitrate absorption. So this is why we have a set here in this drift term. And this white noise term W accounts for random microscopic variations in permeability and flow conditions. And the jump noise models sudden inputs of water, for example, from heavy rain or irrigation that can make nitrate deeper or further into the aquifer. Let's have a look at some explicit numerical simulation. Let's choose a fractional order here, alpha to be 0.8. Diffusion coefficient, lambda, is 0.1. And noise intensity, sigma, is 0.1, and gamma is 0.3. So this is a sigma and a gamma here. The lambda is here. That would be equal to 1. And the nonlinear term, 0.1 times y up to 0.5 times y, representing a range of absorption intensities. And then the domain spatial range X is between -50 and 50 meters over a time horizon, T going from 0 to 30 days. And here is the simulation. If we look at the left figure first, we have time in the horizontal direction and space in the other direction. And the lighter the color, the more contaminant we have. So here it's quite light, and then it's dark in between, and light, and even lighter, brighter here, and so on. And interpretation, this plot here, then we fix on the terminal time here. And then we just look at these intensities here, then the graph of these intensities. So kind of, if you have a three-dimensional picture, you have this coming up. It shows the level of intensities at different position. So some comments, interpretation of that, but I think I will just stop there and take questions. And if there are lots of references afterwards, but I can take the question now. So thank you for your attention. I'll stop there.
Thanks for the nice talk. For questions, please raise your hands. I will call out your name as they appear on my screen. Okay, I don't see any raised hands. If you still have any questions, you can unmute your mic and ask.
Hello, my name is Elena Boguslavska. I just wonder, what is the rationale behind differential inclusion?
Let me go again up to this equation here. This G here is a set. So it means that we have a term here that is a set, so that this partial derivative is, we can only say that it belongs to a certain set of values. And that set of values might depend on y also. So it reflects the uncertainty in the drift of the equation. We don't know exactly what this term is. We only know that is in a certain, for example, interval.
Yeah, but my question is, if you use Levy processes, they can jump, yeah?
Yes, yeah.
So the uncertainty here can be represented with just a Levy process. So adding this sort of set structure probably brings something extra, or you're just using it to avoid some complications with Levy processes?
No, the Levy noise, is included to try to model sudden changes in the environment or in the domain. For example, it could be fractures, it could be sudden discontinuities in the porous rock, for example. Yeah.
But why is this formulation? So this formulation, the set formulation, is coming from the practical applications, or it's some sort of artificial sort of invention just to avoid some technical difficulties?
No. I mean, it is indeed, motivated by this kind of studies of fluid flow in porous rocks, simply.
Okay.
Yeah. Like here in this numerical example.
So there are such questions, well, there are such problems without the noise already, and they are solved in this way. And then this is just a little extra with added uncertainty, with added noise.
You could say that, you know, in practical applications, for example, when if you come to the flow of oil and gas and water in porous rocks, in Norway, when I was in the position at Statoil in Norway, we studied how is the flow of water and gas and oil in the porous rock underneath the North Sea. And then the problem is we know, of course, the physical laws for the flow, but we don't. But there are certain parameters we don't know. For example, the permeability of the rock can vary a lot from point to point. So also there is a need to kind of try to include this in uncertainty in the property of the rock by introducing noise. So at least then the noise enables us to say something about the probabilistic nature of the solution, right?
I see. Okay, thank you very much.
Yeah, you're welcome.
I have a follow-up question. So did you had an experimental case or a real-world data to actually compare the solutions?
No. In this case, this is the numbers are just chosen at to get an explicit example.
I see.
It's not coming from an explicit experiment. No.
I see. So you have a fractional in time terms. I wanted to understand what is the discretization that you're using.
Well, actually, there is no discretization. We are using throughout time-space continuous models, right?
Okay. I'll have to check then your paper on it. So one more. Okay. So this levy this levy noise should have a infinite variance. So are you like truncating it or tempering it?
Well, both the W and the V are really not classical processes. They are stochastic distributions. So to get something finite, we have to apply test functions to them.
Okay.
You see, so yeah, you see. So when we have, for example, this formula for the solution of this inclusion, and then it's just as a formula in S star in general. So to find out what it's really doing, we have to apply a test function to it. It's kind of like in quantum mechanics, right? When you have states which are not really numbers until you start looking at them, observing them.
I see. This is interesting. So the reason I was asking is because in practical applications, I mean, variance needs to be finite. So, but you are able to compute it. Compute it with using test functions.
Yeah. I mean, in some cases, as we saw for d equals 1 and d equals 2, then we actually do have variance. But in general, it might be just the distribution, and to find out what kind of values we get, we have to apply test functions to it. Yeah.
Okay. Can you share the reference for this paper probably?
Yeah, sure. Let's see. Okay, so it goes back. This is from Niels Henrik Abel's work in 1823. Actually, he was the first to use fractional derivatives. So the Caputo derivative that we now call it should actually be called maybe Abel-Caputo derivative. So it's a historical interesting fact.
Mhm.
Niels Henrik Gabel used this to solve a problem in mechanics. The brachistochrone problem, I think it was.
Yeah.
And then and there's a lot of interesting things about that. And then these are papers on Adler is a paper on Levy fields. Aumann it has this definition of integral of sets, valued functions. And the Mittag-Leffler function derivative. Dalang-Walls has also something related to Levy fields. And this is the paper on Mallevat calculus by Dinuno and Troske and myself. Yao Shung Hu proved these mildness results for the equation case. And this is a book by Sverre Holm on fractional derivatives and applications. Here's a book by co-authors and myself on stochastic partial differential equations. And also Ibe is an interesting book on fractional derivatives, or includes that. Let's see what else. Yeah. And we are partly using this paper together with Muley Hachemi and myself, which is from fractional calculus and applied analysis from 2023.
Okay.
Yeah, but you're free to ask me if you have any questions or.
Yeah. But there is still something very unsettling about about it. So having infinite variance in actual physical applications. So how do you physically justify this?
Yeah, the problem comes from the noise. The noise is very rough.
Yeah.
And actually, it's not a process. It's a distribution. And since the noise here and the noise both W and V are distributions, we cannot expect that the solution will be more special than these noises. Or in some cases, it is nicer. And for example, in space dimension 1 and 2, the solution, at least if alpha is greater than or equal to 1, will be in L2.
Okay.
So but to find out what is the value of y of tx, you have to apply a test function to it. You have to look at it with a microscope, if you say, or look at it with observation equipment.
I see. Okay. I'll actually think about it and probably go through the paper as well. And if I have further questions, I'll email it to you.
Yeah, preliminary version is available on Archive.
Okay. Thank you.
Okay.
So do we have more questions or comments? You can please unmute your mic. So I assume no. So this is a good point to close this talk. Thank you again for the very nice talk. It was really a pleasure having you here today.
Thank you. It was a pleasure for me too. Yeah.